Hello and welcome to this video series on statistics and probability. Statistics is about collecting, organizing, analyzing, and interpreting data. Note that data is the key here. So if you are interested in data analysis or data science or in machine learning professions, statistical knowledge is required and it is very useful skill to have. In data analysis, two statistical methods are frequently used. Exploratory data analysis or EDA, which we have previously discussed in many videos on my channel, and inferential statistics. We have seen that in exploratory data analysis, we look at summary statistics, measures of central tendency and dispersion, and we often use visual techniques such as histograms and box plots to inspect the data, understand the distribution, identify outliers, and also understand the relationship or similarities between the data. In inferential statistics, we look at the available data and draw meaningful insights from it. Then, based on the result of our analysis, we make informed decisions. So the goal is to generalize findings from a sample to a large population, and it is fundamental in data analysis and decision making. Data is an essential ingredient in statistics and data science. Data comes from several sources such as experiments, computer simulations, surveys, and field observations. Previously, in another video, we listed sensors, images, text, and videos as data sources, which is also true as field observations can involve sensor data. It can be bunch of images, videos, and surveys can contain forms, that is text information. Computer simulations can also generate data in the form of images and time series sensor data, text, or video data. As a general rule, we can think of the process of generating the data as stochastic. There is a whole branch of statistics dealing with data collection known as experimental design. Luckily, in this series, we won't be doing any data generation or collection. Random experiments are an important part of the probability theory. Random experiments can be defined as experiments that can be performed many times under the same conditions and their outcome cannot be predicted with complete certainty. For example, if we toss a coin, the result of the coin can either be heads or tails, but we cannot say with certainty which one it will be. Another example is rolling a die, where the results of the experiment can be one of the numbers from 1 to 6. Again, we cannot say with certainty which number will be the outcome of the roll. An experiment in probability will have a sample space, a set of events, as well as the probabilities of occurrence of those events. So let's see what these terms are. A sample space is a set of all possible outcomes of a random experiment, and each outcome is called a sample point. In the example of a coin toss, the sample space is a set consisting of heads and tails. And in the example of rolling a die, the sample space is a set consisting of numbers from 1 to 6. Often, there will be more than one sample space that can describe outcomes of an experiment. For example, in rolling a die example, one sample space is the set consisting of numbers from 1 to 6, and another example is a sample space containing of even and odd categories. That is whether the outcome of the roll is an even number or odd number. Let's see another example. What if we roll a die twice or we roll two dice together? Then what will be the sample space? In this case, we will have 36 elements in the set. A sample space can be discrete or continuous. When the sample space is finite, it is called a discrete sample space. And when it is non-countably infinite, it is called a continuous sample space. An event is a subset of a sample space, meaning it is a set of possible outcomes of a random experiment. If the outcome of an experiment is an element of set A, we say that the event A has occurred. In the rolling of a die example, our sample space is a set consisting of numbers from 1 to 6. If we are interested in seeing that rolling a die results in a number less than 4, then our event A is a set consisting of numbers from 1 to 3. And any time the outcome of the die roll is a number that is an element of set A, we say that event A has occurred. We have sure or certain event when the event is the entire sample space. Also, we have an impossible event when A is an empty set, which means that it cannot occur. By using set operations, we can obtain other events in the sample space. A union operation suggests that either A or B or both can occur. Intersection suggests that both A and B can occur. Complement is that anything but A can occur in the sample space. And difference operation suggests that A can occur but not B. A Venn diagram is a widely used diagram style that shows the logical relation between sets. In this diagram, the entire rectangle represents the sample space, whereas events are displayed as overlapping circles. In addition to union, intersection, and difference operations, we can also see disjoint or mutually exclusive events, which simply means both A and B cannot occur together. Let's look at an example of tossing a coin twice. Suppose there are two events A and B. Event A states that at least one head occurs in the outcome, whereas event B states that the second toss results in a tail. So in this case, A union B will contain all possible outcomes, that is, it is equal to our sample space, whereas A intersection B will be a simple or elementary event containing only one element, that is HT. A complement will also contain only one element, that is TT, and A minus B will contain two elements, HH and TH. In any random experiment, there is always uncertainty as to whether a particular event will or will not occur. The probability quantifies the chance that an event will occur. It's a real valued number between 0 and 1, and for sure or certain event, the probability is 1 or 100%, whereas for impossible event, the probability is 0, which means this event cannot occur. There are two important procedures by means of which we can estimate the probability of an event. In the classical approach, if an event can occur in h different ways out of a total number of n possible ways, all of which are equally likely, then the probability is h divided by n. In the coin toss example, suppose that we want to know the probability that a heads will turn up. Since there are only two likely ways a coin can come up, and heads is one of those two possibilities, we can reason the probability that heads will turn up is 1 by 2. In the frequency approach, if after n repetitions of an experiment where n is very large, an event is observed to occur in each of these, then the probability of the event is h by n. So now for the same coin toss example, if we toss the coin 1000 times and 500 of which land heads, then the probability estimate will be 0.5 or 1 by 2. There are drawbacks in both approaches, and because of these difficulties, mathematicians have been led to an axiomatic approach to probability. Probability is a real valued function that assigns to each event A in a sample space S a number such that the following three properties are satisfied. So there are three axioms. Axiom 1 states that a probability of an event A is non-negative. Axiom 2 states that the probability of the sample space is equal to 1. And axiom 3 states that for every collection of mutually exclusive events, the probability of their union is the sum of their individual probabilities. From the axioms, we can prove various theorems on probability, and here we will see some of the key theorems. Theorem 1 states if A1 is a subset of A2, then the probability of A1 will be smaller than the probability of A2, and probability of A2 minus A1 is equal to probability of A2 minus probability of A1. Now let's see an example of rolling a die, and we will use the Venn diagram to explain our sample space as an event A. In this case, the sample space is a set containing numbers from 1 to 6, and event A is a set containing numbers from 1 to 3. So we can see that A is a subset of the sample space as all elements of A are contained in the sample space. From axiom 2, we know that the probability of the sample space is equal to 1. And from axiom 1, we know that the probability of any event is non-negative. In this case, it is 1 by 2, which is smaller than the probability of the sample space. And we can see S minus A is equal to A complement. And if we plug this into the above theorem, we get another theorem that we will see in the coming slides, that is probability of A complement is equal to 1 minus the probability of A. Theorem 2 states that for every event A, the probability is between 0 and 1. If it's a certain event or sure event, meaning it is equal to the sample space, its probability will be 1. If it is impossible event or empty set, its probability will be 0. For any other event, its probability will be between 0 and 1. As we saw in the example of rolling a die, that probability of A was 0.5. Theorem 3 states that the probability of an impossible event is 0. Now let's say for the same example of rolling a die, we are interested in an event that contains elements which are both greater than 4 and smaller than 2. As you can see, this is an impossible event as it cannot occur and the set is empty. From axiom 2, we know that the probability of the sample space is equal to 1. We can also see that the difference operator on S and A returns the sample space S, as A has no elements in it. Then using theorem 1, we can show that probability of A is equal to 0. Theorem 4 states that if A prime is the complement of A, then probability of A prime is equal to 1 minus the probability of A. We have already seen this in the explanation of theorem 1. Theorem 5 states that if A can be written as a union of n mutually exclusive events, then the probability of A is equal to the sum of the probabilities of each of these mutually exclusive events. And in a particular case, when A equals the sample space, the sum of the probabilities or P of A is equal to 1, as we also saw in axioms 2 and 3. Theorem 6 states that if A and B are any two events, then probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Let's look at the Venn diagram for disjoint events or mutually exclusive events. For these events, A intersection B is an empty set, and we get the same result as described in axiom 3. However, when the events are not disjoint or mutually exclusive, then A intersection B is not equal to an empty set, and we need to adjust for the overcounting of probability of A intersection B. The probability of A and the probability of B count all outcomes in A and B. However, the probability of A intersection B is included in both probability of A and probability of B. To avoid double counting, we therefore subtract the probability of A intersection B from the sum of probability of A and the probability of B. Theorem 7 states that if A and B are any two events, then the probability of A is equal to the probability of A intersection B plus the probability of A intersection B prime. That is, event A can be split into two mutually exclusive parts, and then the probability is the sum of the probability of these two mutually exclusive parts. Theorem 8 states that if an event A must result in the occurrence of one of the mutually exclusive events A1 to AN, then probability of A is the sum of probability of A intersection A sub I. Since the A sub I event partitions the sample space for A, every occurrence of A must also be part of exactly one A sub I, ensuring that the sum correctly accounts for the probability of A. Suppose we roll a die, then event A is that the number rolled is an even number. That is, it is a set with elements 2, 4, 6. Since rolling a 2, 4, or 6 are mutually exclusive events that together make up A, so we have three mutually exclusive events A1, A2, and A3. And we can compute the probability using this theorem, which is equal to 1 by 2. Let's now see how we can assign probabilities. If a sample space S consists of a finite number of outcomes A1 to A sub n, then by theorem 5, the sum of the elementary events A sub I should be equal to 1. Now, if we assume equal probabilities for all simple events, then probability of A sub k is equal to 1 by n. And if A is any event made up of h such simple events, then the probability of A is equal to h divided by n, which is the same as the classical approach of estimating the probability of an event. In the rolling a die example that we saw in the previous slide, our sample space is a set consisting of numbers from 1 to 6, and then the event is that the number rolled is an even number. That is a set consisting of 2, 4, 6. So considering this, we can see that A is made of three simple or elementary events, whereas n is 6 from the sample space. Then the probability of event A occurring is 1 by 2, which is the same answer as we got before. Let's look at an example now. A single die is tossed once, and we would like to estimate the probability of a 2 or 5 turning up. We have seen so many examples of rolling a die, and now we know that the sample space consists of numbers from 1 to 6, that is n is equal to 6. We have two events A1, which is if the die turns up 2, and A2 when the die turns up 5, and we are interested in knowing whether A1 or A2 will occur. Previously, we have seen that the event A can be written as union of A1 and A2, that is A1 or A2 or both will occur. Now, assuming equal probabilities, we know that probabilities of each of simple event is 1 by 6, and then using the axioms and theorems that we have seen before, we can see that the estimate of probability of event A is 1 by 3, where A is made up of two simple events and n is equal to 6, so 2 by 6 leads to 1 by 3. With this, we conclude this video and we will continue from conditional probability in the next video. If you liked this video, please press the like button and share the video. And also don't forget to subscribe to my channel. Thanks for watching and see you all in the next video.